Welcome to Unit 3, Exponentials and Logs. We are going to begin this unit by talking about graphing exponentials. Please keep in mind we'll be graphing exponentials through our parent function through transformations. So we're going to start with our first parent function, y equals b to the x. For the first one we're going to look at when b is greater than 1. We're going to look at different growth features. So if we're going to be doing our parent function of y equals b to the x, we're going to start with our table, our xy table, getting that parent done. Now, we're going to talk more about properties later on, but if you remember, if I put in 0 for x, b to the 0 is always going to be 1. And I'll show you that in the next video, and we're going to do a little bit of a discovery-based activity with it too, so you can see why does this always happen. But anything to the 0 is 1. So no matter what kind of exponential function we have, you will always have the point 0, 1, for the parent at least. And then the next easiest value to plug in for x is 1. So b to the first, well, that's just your b value. Whether this is a growth or the next one, which is a decay, we're going to have the same type of parent function for these two. So I'm going to just take a moment here and fill this table in as well. 0, 1, and then I put in 1, and out comes b. Now after that, there's going to be some differences that are going to occur, which is why I separate these two out. No matter, though, whether it's a growth or a decay, my parent function now is always going to be 0, 1, 1b. Now please keep in mind that that's 2 points. 2 points make up a line. These are exponentials. These are not linears. So we're going to look at some other key characteristics of exponentials that will help with what do these physical graphs actually look like. If you truly want to come up with another point, you can start here with your parent function. You can plug in a 2 for your x, and then it's just going to be whatever b squared is. So it could give you a third point to help, or you can go backwards and do -1. Maybe you don't know negative exponents yet. Again, not a big deal. That's going to be part of the next video. But for now, I'm just going to use the 2 points. So going back to if we have a growth. So if I have a growth function, and I know that b is greater than 1, when I graph this, I will always have the point 0 over 1 up. And then since b is greater than 1, so let's say, for instance, it's 2. It would be 1 over 2 up, or 1 over 3 up, or 1, 4, whatever that b value is. But since it's greater than 1, it has to be higher than where it's at 1. So that's why it's that growth feature. So no matter where that point is, it's going to have to go above 1. If I try to plug in negative values, what's going to happen is a negative exponent, if I plug in a negative for x, I'm sorry. If I plug in a negative for x, when I take that base to the exponent, it's going to flip my fraction, which means that I'm going to get values over here when I go in the negative direction, but they're never going to be negative. They just get smaller and smaller and smaller. So if b was 2, when I take it to the negative first, I end up getting 1/2 out. So that's lower than this 1. And then if I keep going, it comes up. That's that growth feature. So there is an example of a parent function for a growth. No matter what value I put in for x, whatever it is impossible to take that b value, take it to an exponent, and ever get a negative number. So I am never going to have anything in this region of my graph. Can't. Because I can never put, when b is greater than 1, I can never put a value in for x and all of a sudden have it in that negative region. So it's always going to be above that region. So because of that, we have what is called an asymptote. An asymptote is a location to where it gets really, really close but can never quite touch. So in this case, my asymptote is that horizontal line. It can never equal 0 or a negative. The parent function, please remember, this is always dealing with the parent function. So I have an asymptote, since it's a horizontal line, it's a y equals line, and it's at 0. All exponentials will have asymptotes. Now I'm going to look at my domain and then my range. You remember your domain are those x values. What kind of values can you put into your x column? I can put in positive numbers. I can put in negative numbers. I can put in anything I want. My domain It's going to be the set of reals. My range is different. Now I have to look at what's happening with my y values. What kind of output values am I going to have? It might be easier when we start looking at specific examples, but in this case, my range is all those possible y's. So if you look at my graph, I never once cross below into this negative region. My y's can never be in this negative spot. My y's start just above my x-axis and go up. So for my range are my y's. So it's a set of all y such that y is greater than 0. It's not equal to 0. There's an asymptote there. An asymptote means it never quite touches there. So it's just above that 0 value. So that's going to be my range for those. Now, if my b value is greater than 0 but less than 1, this is going to be a decay feature. So again, in this case, b is greater than 0 but less than 1. So I have that point, 0, 1. So there's my point 0, 1. So my next b value has to be between there. So for instance, a half. So it'd be 1, 1/2, or a fourth, or a third, or 0.1, a tenth, whatever it is. So at 1, it's going to be below that value, which is why it's a decay. Same process as before. No matter what value I put in for x, my outcome value, my y value, is never going to be 0 or negative. It can never be 0 or negative. My x's can be. Domain. My domain are my x's. I can put anything I want in for x. My range, however, cannot go below. So in this generic case, I again will have an asymptote at y equals 0. Draw that asymptote in wherever it occurs at. For the parent, again, it's that line there. So there's my asymptote. My domain, just like before, is all reals. My range is a set of all y such that y is greater than 0. This is for my parent. All of this work is just my parent function. And then we're going to do some transformations with it. Okay. So each time we're going to do a transformation, maybe do the first one with me, but then after that, pause it each time you get a graph and see if you can do your parent function and then the transformed one. So here's our first example. Graph y equals 2 to the x. This is already the parent form. There's no transformation taking place. Remember, your parent is y equals b to the x. My b value is my 2. That's my base. My base is 2. So with this process, I'm just doing my parent. My parent function is always plugging in 0. 2 to the 0 is 1, always, no matter what. And then I'm going to plug in my 1 for x, and 2 to the first is 2. There's my 2 points. Again, for that parent piece, if you want to go one more out and put a 2 in there, 2 squared is 4, it might just make it a little easier to see how quick it's growing versus just those 2 points. Minimally, you need 2 points. The more points you have, the more you're going to be able to see it. So I graph this, 0, 1, 1, 2, and then 2, 4. So you can see that jump up there a little bit more. You can put in another one, put in 3, so then I'd have 2 to the third, which then, of course, is 8. So it kind of keeps going through that process. I know there's an asymptote always. This is my parent. It has not shifted anywhere. So I have a horizontal asymptote at that y-axis, at the x-axis, excuse me. Horizontal asymptote at the x-axis. And I connect my dots. And I have this parent. So each parent is going to be just a little different based on its base. Whereas when we did quadratics, we did absolute value, the parent was always exactly the same. In this case, it's not. It's completely based on what number you have as a base. I can go through this. My domain, all reals. My range, set of all y's such that y is greater than 0. And then I can also find, in this case, my x-intercept. How about y-intercept? Is there a y-intercept? Yes, there is, because I've misstated that. I'm sorry. My y-intercept is at 0, 1. My x-intercept does not exist. My x-intercept does not exist because there's a horizontal asymptote there. Based on our shifts, we can get both. So pause this just for a moment, see if you can pull out your parent function, and then we'll start doing some transformations with it. So my parent function is just the base. It does not have anything to do with multiplication. It does not have anything to do with addition or subtraction. So I pull out that y equals 4 to the x, and I always know I have the point 0, 1. And then I plug in 1 for x. When I plug 1 in for x, my outcome value is 4. I can also plug in 2 for x if I want one more. And then 4 squared is 16. That jumps quite a bit. I could also go negatively, put in -1. If I put in -1, I'd get 1/4 out. So this is the parent piece of it. I'm just figuring out what my parent function is. Then, once I find my parent function, I can now do my transformed function. This is an example of either a stretch or a shrink because we have a multiplier of a half. Whenever we have a multiplier, it's going to either stretch it up or shrink it in. Okay, that's always the feature of the multiplier that we call an A value, which you'll see later on when we start writing equations. So now what I'm going to do is I'm going to find the graph of my transformed equation based off of my parent function. Now you have to look at how is 1/2 attached. Is 1/2 physically attached to x, or is it actually attached to y? If it's attached to x, it has to be with x, either physically right next to it being multiplied to x, or added or subtracted to the x value. So in this case, it's in the front of it, which means it's actually attached to y. So there is nothing that's happening to my x values. So my x values are going to be the same, 0, 1, and 2. They come from your parent table. My y values, however, are going to differ. My y value before was 1. I take that 1, I multiply it by a half, so my new y value was 1/2. Now I take my next y value of 4, I multiply it by a half, and I get 2. The same thing with 16. I multiply it by a half, and I get 8. So now I can graph these. And now that I have my points on here, I have not physically shifted this anywhere at all. All I did was stretched this. So there's a horizontal asymptote at that x-axis. So I need to make sure when I connect my dots, I do not go past it. I'll do my best here. And then it shoots up, and it keeps going in both directions. It shoots up very quickly because that second point is already up at 8. So there's a stretch or shrink feature. That's going to just strictly deal with that multiplier in the front. So here's going to be another multiplier. Try this one on your own completely. Go through the process and see what happens. So pulling out the parent function, 0, 1, 1, 5/2. You could go forward and do 2, which is 25/4. I'm not sure how much that helps you. Or go backwards to do -1, which would be 2/5. Because my base is 5/2, it's greater than 1, this is going to be a growth. This is going to be a growth. However, it's going to be odd because of this multiplier of a -1. So the -1, it's not directly attached to your x. It is physically attached to your y. So all my x values in this case stay the same. My y values, however, multiply by -1. And now I'm going to plot these. This looks kind of different. This might be a case where if you couldn't see what happened, maybe you pick a couple more x values so you can see what happens. But what happens is I had a negative multiplier. The negative is affecting my y's. Whenever the negative's affecting my y's, remember, it's reflecting over the x-axis. Because it was up, and now it has to go down because those y values are saying, nope, we have to be negative. I have not physically shifted this up or down at all. So you still have a horizontal asymptote at that x-axis. So I got to make sure I don't cross that. So I'm going to connect those dots, and I know what happens towards asymptotes. It gets closer and closer, but never quite touches. So again, this is a growth. It's just a reflection over the x-axis. The next one that we're going to do is going to deal with transformations in terms of translations. We are going to be sliding these left, right, up, or down. I'm going to do one translation, and then I'm going to throw everything together so you can practice this. Again, look first at your parent function. Graph that out, or find what that table is separately, then we'll do the translation. I picked an extra point in here just so that you can see because we are going to be shifting this around. Those 2 points might be kind of hard to see. So now that I have that, now I'm going to find my transformation graph. There's a +2, so this is the transformation. This +2, is it attached to your x or is it attached to your y? It's attached to your y. It's not as an exponent. If it said with an exponent of plus 2, that would be affecting your x values. There is nothing attached to your x values. So in your transformation graph, 0, 1, and 2 do not change. Now I'm going to look at my y values, because the y values do change. The y values, it says plus 2. Keep in mind, what's attached to x is opposite, what's attached to y is the same. So each of these y values in this y column are going to add 2. So it was 1, it's now 3. It was 3, it's now 5. And it was 9, it's now 11. So now I have my new graph that I can plot these points. So there are my points. Keeping in mind what happened to this graph is all my y values moved up 2. That's truly what happened. Is all my y values physically moved up 2 spots. Normally in my graphs, there is a horizontal asymptote. That horizontal asymptote is the equation y equals 2. Or y equals 0, excuse me. Y equals 0. All of my y values moved up 2. Therefore, the horizontal asymptote that used to be y equals 2, 0, is now 2. It moves up 2 units. Because every y value physically moves up 2. So now, instead of my horizontal asymptote being at y equals 0, being that x-axis, it now is up at 2 because of that translation. So now what I'm going to do is connect my dots, and I have the transformation. Look at what's affecting your x values, look at what's affecting your y values, and my big tip is take a look at what is adding or subtracting to your y's and put that asymptote on there right away. That way you don't miss it and you don't accidentally go in the wrong direction. So here's one I want you to be able to do all of it. It looks a little bit scary maybe, but what I want you to do is pull out that parent function, y equals b to the x. That's it. Then we've got 3 different transformations that are taking place here, and we'll take a look at all of those individually. So to start with, I would like you to make your parent function table. Then we will come back together and you will do all of them. So I have my parent function. I started with 3 values, again, just so that you can see it a little bit easier of what's taking place. As I had recommended earlier, at this point, if you can, pull out your horizontal asymptote. Normally it's at y equals 0. Is there anything adding or subtracting to your y? The -3. Which means my horizontal asymptote is going to drop down to y equals -3. So I know I have a horizontal asymptote there. So at least it gives you something to work with. If you don't do that right away, it's not a big deal, but it is helpful to do that. So now what I'm going to do is I'm going to make my table. I'm going to look at what all is affecting my x values. If it's affecting my x values, it's physically attached to x. That's the only thing that's attached to x. There's no multiplier for the exponent. It's only x minus 1, which means all of my x values, remember when it's attached to x, it's the opposite. So since it says x minus 1, all of my x values are going to actually add 1. So in my table, all of my x values are going to add 1. So it was 0 plus 1, so that's 1. 1 plus 1 is 2. 2 plus 1 is 3. So my new x values are 1, 2, 3. Now I have to look at my y values. There are 2 distinct things that are taking place with my y values. The first thing that's the one thing we already talked about is the subtracting 3. But the other thing that's taking place with my y values is this 4. That 4 is a multiplier on your x, on your y, because it's not up there with the x. The 4 is a multiplier to your y. So there's a multiplication going on with y, and there's a subtracting going on with y. Remember with y, we do exactly what it says. We do that order. So multiplication, addition, and subtraction. What do I do first? Multiply. So I take that y column, and I'm going to take each of these individual items, multiply it by 4, and then subtract 3. So it was 1, times 4 is 4, minus 3 is 1. And then I'm going to take my 2, multiply it by 4, which gives me 8, subtract 3, which just gives me 5. And lastly, 4, multiply by 4, which gives me 16, subtract 3, which gives me 13. I have the new points to graph. Plotting these, 1, 1, 2, 5, and 3, 13 is off the grid. It may have been helpful to go backwards and have done in my x column a negative 1. I would have done a negative 1, I would have had a half. I would have some numbers that are a little bit smaller, a little bit closer. But because I know my asymptote shifted down 3 units, I now play connect the dots. I know what happens towards my asymptote, and then I know this shoots up. Again, if I would have went in that negative direction, you would have seen it get closer to the asymptote. That's part of the reason I recommend physically putting that asymptote on your graph. So now I can go through all my different pieces of information. There's a horizontal asymptote, HA. At y equals, because it crosses your y-axis, we shifted that down negative 3. We did that right away. You can always do your horizontal asymptote first if you want. I look at my domain. What kind of x values can I have? If I go along here, any place where I can't have it? Nope. So it's all reals. Then when I look at my y values, what kind of y values can I have? I have all of those and going up, keep going down, stop. Can't go any further. So therefore, for my range, it's a set of all y, such that y has to be greater than negative 3. It has to be greater than your horizontal asymptote because it's opening up. It's growing vertically. So that's putting everything together. I have one more graph for you to do. I'm going to put it up, and then I'm going to show you just what the answer is with all of the work along the way and see how you do. So here's my parent. So I found my asymptote. I fixed my x and y values based on their parents, and then plotting the points. I have those points. This is a decay because my base is a half. So as x gets larger, my y value approaches negative 2 versus shooting off to infinity. So there's a graph using the 3 different transformations you will be looking at with exponentials.